Okay, thanks. And thanks for being here. Thanks mostly to George, who made contact with me when we were working on the metal poor star survey at high resolution, and then gradually pulled me into the RR Lyra stars. Uh, it's the first time I realized stars go up and down, right? Okay, so here's what I want to talk about. Um, eh, there, there are going to be some talks today that are really good, but their focus is different. They are talking about the application of RR Lyra stars to galactic and even extragalactic dynamics, distances, stuff like that. And of course, those are crucial uses of RR Lyra stars. But what I want to do is basically continue George's theme. I'll be stepping outward from the 15 minutes, but I'll be talking about things that happen within an average pulsational cycle of an RR Lyra star. And so what I'll be focusing on entirely is one data set, and that's the set that George briefly mentioned in his talk. But probably 8,000 spectra were gathered by George for sort of what's coming up to be maybe about 30-ish stars by now. But the point is observed intensively. And that's the big deal here. And that had never been done before. We first got the spectra from George for a sample of about 10 RR Lyra stars, for which he had collected on average 200 short integration spectra. And that, of course, I'll have more to say about that again. But let me just give you the first result, I guess, from the Texas point of view. We care about chemical compositions. And George kindly handed the spectra to me and my graduate student, Beijing 4. And
she actually came and observed at Las Campanas and gathered.
Oh, that's right. Yeah, I forgot that. Yeah, thanks. And so a summary from her PhD talk is that we showed for the first time ever that you can get the exact, very similar chemical composition results, no matter what phase of an RR Lyra star you're dealing with. On the left, we show metallicity. We show the main physical parameters: temperature, gravity, metallicity, microturbulent velocity. And the important point here is, I knew I'd do that. The important point here is that the raw metallicities are roughly the same, no matter what phase you use. Even more impressive is the fact that for most species, not all, but for most species, the species to iron abundance ratio, or the element to iron abundance ratios, are just rock solid the same. And this was a big improvement over what had been done previously, which is to basically take longer integration, high resolution spectra at phases that may not have been the best. We use this in a paper led by Miriam Shadid to try to redefine, as much as we could, the basic delta S scale. And Leiden's scale is based on delta S, or it's an improvement of the original delta S. And what we showed is the Carnegie spectra really help calibrate that, redefine it, and basically, outside of a small tilt, it sort of reconfirms the delta S. That delta S actually really works in detail. On the right-hand panel, what we want to show, the black and the red dots, details are not important now, but these are the RR Lyra stars. And what we're showing here is that the abundance ratios in RR Lyra star are greatly similar to things you would get, abundance ratios you would get if you're studying galactic populations with non-variable stars, the classic main sequence, the classic red giants. You get the same results. So RR Lyra stars can be used for that. So that was the result of Beijing's work and Miriam's application. Alongside it, we created something which has turned out to be useful for other investigators. That is a typical set of temperature, gravity, velocity profiles with phase. Now, the caution here, and it should be, you've got to keep in mind, that these are based on LTE analyses of stars that aren't moving. And so be careful, folks. But the point is that the correlations are very, very usual, if you might say. You can use these as long as you accept the input assumptions that we're basically trying to link these to LTE atmospheres. You can use these, and they actually work pretty well. And they have been used by people like Giuseppe may talk about this in his work, universal applications. Okay. Finally, the other thing that has become clear, first with Beijing's work and subsequent analyses, is this, that a lot of what you might call old classic or Lyra high resolution spectra seem to choose the phase of minimum light as probably the best bus. And that's sort of 0.5, 0.6, something like that. Whereas really, if you want narrow line profiles, if you want the calmest Lyra atmosphere, it's sort of near 0.4-ish. That's the phase you should use, as I'll show again. Okay, but that's enough for the metallicity stuff. What George has pushed me into in recent years is the details, as he showed dramatically with his talk, but the details of what's going on in different phases. And for that, George mentioned it, but here's another example of we co-add the spectra. If you think about it, the 200 spectra for the original set of 10 Lyras means that you could really get a lot of spectra at basically the same phase in, say, every 0.05 jump in phase. You can actually stack the spectra to get something which a traditional stellar spectroscopist would say, I can analyze that. Okay, whereas good luck, folks. Again, so for this particular one, I've summarized that the typical co-addition stack has a phase range of about 0.03 or something like that. The exposure times always are less than 15 minutes, so you don't get phase smearing. And these are simple co-additions. No cleverness was assumed here. Okay, but using those, then what do we care about beyond metallicity? Well, the first thing that we worked on, George worked on and got me to do this, is do our Lyrae rotate? And I'll have a summary slide which justifies why the question was asked by George. But here's the fussing details from that work. So there's a paper in which we tried to estimate the rotational speed of an Lyra star. And the problem is that these profiles are subject to many broadening mechanisms, starting with the instrument itself. The top panel just shows that if you have no instrumental broadening, if you have just the stuff that would come out of a synthetic spectrum program, then clearly that doesn't match the observed points. If you add the instrumental broadening, though, it almost matches. And so we're trying to fight beyond that. And in the bottom panel, you see the problem. What we've done here is we have added, in addition to the standard thermal and microturbulent velocity effects, and the instrumental effects, we said, well, what if you have it rotate? And what if you have just pure macro turbulence? And combinations of rotation and macro turbulence are almost indistinguishable when the rotational speed is small. And so it is so difficult to measure them that basically a quantity that George called V mac rot is what is actually coming out. Fortunately, there are easy regularities in this. First off, if you simply plot full width half maxima of typical metal lines at different phases, you can easily see that it is changing. Right, and again, here's the sweet spot is also the sweet spot where you have the smallest full width half maxima. And if you didn't do a bunch of stars and you plot them together, metal poor, metal rich, where metal poor and metal rich are cut at about a metallicity of -1. We're not going to argue about the details of where that cut should be, but there is a great regularity in the line broadening that is due to rotation plus macroturbulence. And since I'm afraid George had to point this out to me, rotation should not vary with our Lyra pulsational phase. Okay, yes, oh, duh. And so what you want is the minimum of the combination of macroturbulence and rotation. That is as best you can, good as you can do to get the amount of possible rotation. That's a maximum for the rotation. Okay. And there are details. If I had an hour instead of the 20 minutes, I might fuss at these details. But they're interesting in their own right. First off, the RRC stars. Yeah, they milder pulsations, not much evidence of shock waves, but there is still a tendency to have roughly the same sweet spot of phase where the lines are narrowest. And the rotational velocities you get from the RRC stars, the minimum of those rotational velocities is sort of kind of like the minimum of, or the macrot, the minimum you get from the RRABs. Well, more to say about that in a minute. And also stars with Blaschko effect, that annoying long-term modulation of the pulsational cycle, you still get the same thing with the Blaschko stars. And more could be said about this, but let's press on. Now, if I had an hour instead of 20 minutes, I could spend the rest of the time on this one plot, because the point is this sort of drives the question that why George was interested in rotation of our Lyra stars, because it had been known a lot in the past. Ruth Peterson did a lot of work in this area, but others contributed also to point out over and over and over again that the blue horizontal branch stars, all these things, often are rotating very rapidly. Not always, but often. So here's a bunch of just stars, and I could, if you go look at the paper, you'll see where all the sources are for those velocities. But these aren't subtle. They can be 20, 25, 30 kilometers a second. Here are the RRAB stars from here to here. Here are the RRC stars, which appears to be sort of the transition stars. And here are the the red horizontal branch stars. And there's a whole story about this decline here. But the important point is, and again, the small summary here is that the minimum seems to occur at RRAB stars. And of course, since a lot of this has to be macroturbulence and not rotation, the rotation is probably down here someplace. So how come all these stars are like that? They go through the instability strip, folks. So how come all is quiet? Okay, so that still is to be determined in the future. So let's go back. I just want to remind you again that what is done often is to take up to 200 individual spectra of an RR Lyra star and compress it into up to say about 20, 25 sort of co-added phase points, okay? So I'm going to show you one star for what we're working on now. After we published the rotational thing now, and now we're going to work on the following. So if you just look at the co-added spectra, and if you just stare at them long enough, as we have, when we're trying to measure equivalent widths, and folks, if you haven't done that by hand, it's not fun. It's probably about the most boring thing you can do in life. So, but you start noticing that the line shapes not only get broader, the lines get broader and thinner, but they also start to distort in they're not pure Gaussians anymore. And you can look at here at WIN, and you look at three phases. There's the best. And then there's a 0.6 and a point and 9. This is the kind of, oh, I shouldn't point the pointer at you. He should light up. Sorry. So that's the phases George was interested in the rising light and maximum light phases. And I think you can see, I'm stalling enough so you can see, yeah, I can see those lines are distorting left, distorting right, and they're nice and sharp at 0.35. Fine. But we decided right away that in order to really do the line shapes, even the co-added spectra by themselves were insufficient. What we needed to do was co-add individual line profiles in the co-added spectra. Okay. And here's a mock-up of what we tried to measure. So here's one of the WY ant, and I'll show you a larger view of it in a minute. Here's a WY ant, and these are co-added, I think 71. I'll show you that in another slide. There are about 71 stacked line profiles that produce this average one. And what we measure is something simple. The half width, half max, the half width at about 0.15 of the continuum, because I could tell you at coffee break why we chose that. What we do is red and blue asymmetries, line width, skewness, blue, red. So here's the, trust me, you can count them. There are 71 of the faint lines in there. And I haven't done any normalization other than just zero them at their line. The other thing is we chose the central or the deepest line point to normalize everything. We know that's not perfect, but it's close enough. The black solid line is the co-addition of all 71 of them. And we have the ability to say, well, what about just the strong lines? What about just the weak lines? They give basically the same answer. Basically, the photosphere where the metal lines are formed is sort of the photosphere, and it's not that big a region, so it's not surprising that the weak and the strong lines sort of show the same profiles. So now let's look at WY ant and go back to the Sneden paper. And in the Sneden paper, and that all of the stars that we're going to be working on are actually shown. This triplet panel is shown for each one of those stars, and it's just showing what had been accomplished up to the Sneden paper. Clearly, the photometric variations from ASAS are shown here, and George's measurement of H alpha flux is shown there, and the H alpha velocity profile over the whole phase range and the metallic line profile are shown over the phase range. So when we look at the line shapes and the line profile distortions, here's how they correlate. So, I'm sorry, one more slide first. So these are just, now you can see it pretty easily. Your eyes can say, hey, wait a minute, the red skew, the blue skew, those aren't that difficult. That's why 0.35, 0.66, and 0.95 were mentioned in the previous slide. And our measurements are simple. The number of lines in each edition are given here. They can be up to about 90-ish. Minimum is about 20 when the lines are really distorted, because the profiles start running into each other and you have to reject some, blah, blah, blah. Okay. But in other words, you can easily see how they're changing. And like everything else in our libraries, they're changing calmly the same way over n cycles, where n exceeds our lifetimes. And the point is that I put the photometric variations up here. Again, that's ASAS data. And now I've just shown the difference between the red and the blue half widths at the half power point and at the 15% power point. And they're following each other. Are they the exact same phase where this max is this max? No problem. No, we have to work on this a little bit more. We have to have more stars, but it's getting there. Okay. Well, what if you use something which is more mathematically sophisticated, which I just learned a couple of years ago? Skew. I'm proud of myself. I actually know how to do this thing quantity now. Usually I'm limited to standard deviation on a good day. So, but there's no new information. Well, I'm sure there is once we look at it, but to first approximation, it's the exact same answer. And it's correlating with the photometric variations of the star, okay? We've done 5 stars so far. The frustrating thing, I'm glad my time is over. The frustrating thing is George wants me to do 20 more of these, and those aren't happy days, George. But you know what? I'd be very surprised if they don't yield the exact same
But you have to do metal rich versus metal poor before I believe you.
Look, I got a metal rich. Take that. Sort of. No, but George is exactly correct on that. We've got it. We will separate. We'll have enough to separate, pardon me, the metal rich from the metal poor. We will do the RRCs. Yeah. And the RRCs, we, of course, confidently predict, I hope, that the variations, the line shape variations will be substantially smaller, but we'll find out. So what I wanted to emphasize is that the DuPont spectra have yielded a set of RR Lyra closely watched phases that I still have a lot of secrets that we can uncover. I went too fast in the previous slide, but all of George's spectra are absolutely public, which is another way of saying, if you don't like our analyses, you go do them yourself, because all the spectra are there. And Giuseppe has been using those spectra, Giuseppe and his group. So there's a lot to be gained here. We've found out a lot, but there's more to come. Thanks, folks. Questions from the room? Now? How about now?
How about now? Yeah. Okay.
Thank you. Chris, that was a very interesting talk, especially about your plot of rotation speed and effective temperature.
Yeah.
With the
That was
RLIs.
fun.
Yeah. These are all field RLIs, correct?
Correct.
Right. So is there a chance we can do globular cluster RLIs to get a better idea of the impact of evolution from the horizontal branch, to the
It
instability
could be.
strip?
There's a paper by Davide Magurno in which he and I might be stealing some things that Giuseppe wants to say, but he worked on both a monometallicity cluster and omega sen. And a lot of the line profile stuff is actually in there. The interesting thing about their work is they were using a multi-object spectrometer. And so they were getting random phases. Here's our Lyris and they're all where they all are. But the point is the groundwork that was done with these spectra showed that you can work with those. Doesn't matter. You don't need an exact phase.
Heather?
Could you go back to the slide where you showed the basically the alpha to Fe over do you know the individual abundance patterns against the pattern in the galaxy? Was one of your earlier slides.
Oh,
That one.
do you
that
mean
one.
that? Oh, sorry.
Yeah. Now look at like scandium and titanium. Should I worry about the metal rich stuff there, or is that more
Well,
likely?
I think you should, because that means I don't have to anymore. Yeah. No, actually, there's a multi-pronged answer to that. One is that, yes, that we have worried and fussed about that for ages, and we can't make it go away. The other
Interesting.
answer is that Karen Lind is doing a huge amount of work on improving the basic analyses for things like low metallicity red giants. And a lot of that, I bet you, needs to be applied to the RR Lyras also. There are some species I trust, and others I think all they gained me from doing them was extra charges for a journal plot, right? Because I don't pretend that they are good.
So
Yes,
stick
but
with
you are correct.
calcium.
Your basic objection is correct.
Yeah. Okay.
Right.
Thanks.
So I'm venturing to ask, in this plot on the right, are the more deviant measurements for species that are more gravity sensitive than others?
I'm pretty sure that is true.
I would
And
love
our
to-
gravity estimates are purely ionization balance. And come on, for an RL-IRA star, they can't be right. There's no way. And they, by the way, they all, when you do have a situation where you have a cluster, they're all, the ones you get from ionization balance are always small. Let me try that again. The gravities you get from ionization balance are always too small. And not a huge amounts. And for what we're using for, we could get away with it. But yes, worry about that.
But that's also very, what you just said is very consistent with the fact that something that nobody measures anymore is the bomber jump. And those predict log Gs that are much lower than your dynamical log G would be. And I'm wondering whether all of this.
Yeah, it really needs to be done with modern physics. I mean, seriously, that's, and thankfully, especially in Europe, people are worrying about this. Karen Lind, Maria Bergamon, you know, they're leading the next, you know, analytical wave.
All right, we have a question online from Giuseppe. I'm going to ask the next speaker to come up and transition as Giuseppe asks the question.
Thank you very much for the opportunity. Chris, obviously it's very interesting. I would like to go back to two of the slides that you showed. One is about the rotation. Because in my opinion, there is something interesting there. I fully agree that the perfect laboratory is a globular cluster, but you know, the fact that we have the B stars that are look like more as red horizontal branch stars, and the C-type that look like more as blue HB stars is probably suggesting something about the direction of the evolution during the off-ZAB evolution of these objects. So it might be, once again, the possibility to have a good sample. I don't know whether Omega Sen is the right laboratory to investigate this issue, because we have a mix of different metallicities. But for those ones that are more simple, we might learn a lot of new things about the fine structure of the evolution inside the instability strip. So this is the first point. The second one is, I was wondering whether the kind of analysis in microturbulence velocity and rotational velocity, do you have in your sample meta-rich objects? When I am saying meta-rich, obviously I am saying something that is approaching solar or something like that.
I think you're, Giuseppe, as I understand you, you're asking about metal-rich objects with Carnegie spectra, DuPont
Yes,
spectra.
exactly.
The answer, yes, they go up to solar metallicity. Not many of them, one or two, but they're there.
And they have the same trend compared with all the others. They do not show any peculiarity concerning the variation along the pulsation cycle.
Yeah, as far as we can tell, Giuseppe, yes, same trend. And of course, I have not done anything except anything more metal-rich on the line shape work beyond minus 0.9, but we will be getting to the ones that are near solar that you're more concerned with.
Okay, thanks a lot.
Thank you.
Thank you, Chris. Let's thank Chris again.